Today we are looking at integration techniques. We are looking at integration techniques. These are going to help us when we are trying to simplify complex integrals, especially when you're dealing with the U substitution. So I'm just going to do a few. I'm going to formulate few general formulas that you can use to work on any complex integral. So if you are given an integral, we have seen that if you are given an integral of this form, root a squared minus x squared dx, this is sine inverse x over a plus c. Or if you are given an integral of this form, a squared minus x squared dx, here we have a squared over 2 sine inverse of x over a plus x over 2 root a squared minus x squared plus c. So I'm going to continue to formulate other formulas that you can use to work on integration techniques. So the first one, what if you are given an integral in this form y1 over a squared plus x squared dx? Obviously a is a constant. Right. So if you're given an integral of this form, what is the easier way of doing this? So we are going to sort of like derive a formula or an expression that we can just use to evaluate an integral like this one. So we are going to say we are going to use substitution whereby say let x to be a tan theta. So now your integral is 1 over a squared plus, where there is x, you substitute a tan theta. So it's tan theta squared. This is dx. And since now your variable is in terms of theta, so we'll come here and say dx d theta is equals to a sec squared theta, right? Which means dx is the same thing as a sec squared theta d theta. So where there's dx here, you substitute this. So your integral 1 over a squared plus a tan theta squared times dx is what? It's a sec squared theta d theta, right? So you can further simplify this. You're going to have, so if let me just work this out. This is going to be a squared tan squared theta a sec squared theta d theta. So if I factor out a in the denominator, I'm going to have a squared 1 plus tan squared theta times a sec squared theta d theta. And here we know if you use the identity 1 plus tan squared theta is equivalent to sec squared theta, right? So we are going to substitute sec squared theta here based on that identity. So the integral of 1 over a squared sec squared theta times a sec squared theta d theta. And then from here you can see that this can divide each other, right? And also this, so you're left with the integral 1 over a d theta, and then this integral is going to be 1 over a integral of d theta, which is 1 over a theta plus c. But then we come back to this expression. We want to make theta the subject of the formula. So we say tan theta is equals to what? So tan theta is going to be x over a. Therefore, theta is equals to tan x over a, right? So now here you're going to have 1 over a. Then theta is what? Is tan x over a plus c. So now we have seen that the integral of 1 over a squared plus x squared dx is equals to 1 over a tan x over a plus c. So if you are given an expression in this form, you know that you can just substitute. If you know the value of a, you can just substitute the value of a here and here so that you can get the integral of that expression. So this is one of the main integration techniques that is normally used. So now we have seen the first one. Now I'm going to do the ones for hyperbolics, where we substitute using hyperbolics. So if you are given a case whereby let's say maybe you are given you are tasked to integrate expression like this, or integral of 1 over root 1/root x squared minus a squared, also the root x squared minus a squared dx. So here we are going to, in order, if you're given an integral in this format, you need to know this integration technique. So we're going to derive another formula so that we can simplify this. So you're going to say let x be a cos theta, and dx is going to be what? A sin theta d theta. So here I'm going to start with this one. So the integral of 1 over root, where this x, we substitute a cos theta. So a cos theta squared minus a squared. And then this is there's dx here. So instead of dx, we're going to have what? We're going to have, instead of dx, we're going to have this, which is a sin theta d theta. So here we are going to have, if I simplify this expression, this is going to be a squared cos squared theta minus a squared a sin theta d theta. And again, we factor out a squared from the denominator. We are going to have 1 over root a squared cos squared theta minus 1 a sin theta d theta. So we are going to use this to simplify the denominator of the integral. We are going to use this identity, sin squared theta plus cos squared theta is equivalent to 1. So which means cos squared theta is equals to 1 minus sin squared theta, right? And sin squared theta is equals to from this one. Oh, no, I made a mistake, sorry. It's cos squared theta minus sin squared theta is equivalent to 1. Yes, such that sin squared theta is equals to cos squared theta minus 1, right? So instead of cos squared theta minus 1, we're going to substitute sin squared theta. So the integral of 1 over root a squared sin squared theta A sine theta d theta, and then evaluate the roots. You're going to have 1 over A sine theta times A sine theta d theta. So this will divide, so you're left with the integral of d theta, which is equals to theta plus c. But then your question is, what is theta? You come back to your original expression, which was this, right? So from x is equals to a cos theta, let's make theta the substitute of the formula. So cos theta is going to be x over a, and then theta is going to be over a, and then therefore the integral of 1 over root x squared minus a squared dx is going to be what? Is going to be cos inverse of x over a, right? So this is another integration techniques that you have to know. And what if you are given this form whereby you have the integral of root x squared minus a squared dx? So again, here we are going to use, let's say x is equals to a cos theta, right? And then you substitute there. So we're going to have root a squared cos squared theta minus a squared dx. But then we need to deal with dx. So dx is equals to dx over d theta is equals to what? A sine theta. Therefore dx is equals to a sine theta d theta. So here you're going to have the integral of a squared. I factor out a squared, and I'm going to have cos squared theta minus 1, and then d theta is going to be a sine theta d theta, right? And then again here you're going to use the identity. I'm going to use this identity. So this is going to be root a squared sine squared theta times a sine theta d theta. So if you evaluate the square root, we are going to have a sine theta, a sine theta d theta, right? So this is going to be a squared, because this will multiply, which is a squared, the integral of sine squared theta d theta. So from here, remember, we cannot evaluate an integral of a trigonometric function with the power more than 1. So we need to simplify this using the double angle integrals. So remember that cos 2 theta is equals to 2 cos squared theta minus 1, right? And also this is the same as 1 minus 2 sine squared theta, right? So we want to make sine squared theta the substitute of the formula. This is going to be sine squared theta is going to be 1 minus cos 2 theta over 2. If you make using this, if you make sine squared the substitute of the formula, this is what you get, right? So now we have reduced the power of the integral to 1, so we can substitute here. So a squared, the integral of sine squared theta, now we are going to have 1 minus cos 2 theta over 2 d theta. So here we can just factor out half, so you have a squared half the integral of 1 minus cos dx, right? So this is where we are. So now our task is to evaluate the integral. is to evaluate the integral of this. So this is going to be a squared over 2. Then we need to evaluate the integral. So you need to remember the integral of all the hyperbolic functions, of all trigonometric functions especially, so that you can be able to work this through. So at this point we are saying we have this is going to be, so if you're integrating one we know that it's going to be theta, right? And then theta is going to be, and then theta minus, this is going to be sine 2 theta over 2 plus c, isn't it? So this is what we have, right? This is what we have. So so from here we have this, right? So this is sine 2 theta. So we need to break it down again. So we know that sine 2 theta is equals to 2 sine theta cos theta. The reason why I'm breaking this integral down, because remember initially we were given this integral in terms of x and a, but now we have theta, so we need to simplify it into a form whereby where there's theta we can substitute an expression that has a and x. So here we are at this point. So now let's come back to theta. Remember, we can get theta from the expression that we declared at the beginning, that x is equals to a cos theta. So we know that our theta is what? So we know that theta, let me just write here. So theta is equals to cos inverse of x over a, right? That we know, isn't it? And then now when we come back to this, we are saying we know again here that so we have 2 sine theta cos theta, right? Then from here we know that cos theta is equals to x over a, right? From the same expression, cos is x over a. So here we are going to have this is equals to 2 sine theta. Where there's cos, we are going to have x over a, right? And then what about this one? What about sine? So sine is easy. We are going to use this identity that we used. We are using the same identity, just making sine the subject of the formula. So sine theta is going to be root cos squared theta minus 1, right? So that's what you are going to substitute here. That's what you're going to substitute here. So here you're going to have root cos squared theta minus 1 times x over a, right? So this is still sine 2 theta, and then here we know about cos, that is what? It's x over a. So cos theta is x over a. So this is sine 2 theta is equals to root x over a, right? Squared minus 1 multiplied by x over a, right? So if I simplify this is the same thing as this would be the same thing as sine 2 theta is equals to the x over a root x over a root x squared minus a squared over a, right? If you simplify this is what you're going to get, isn't it? So from here we can, from where there is sine 2 theta, we can substitute this expression, because now this expression is in terms of x and a, right? Which are the initial variables that we're given. So from here we are going to have this is equals to a squared over 2. Where there's theta, remember we substitute. Where there's theta, we substitute this expression. So this is cos cos inverse of x over a, right? And then minus 1 over 2, where this 1 over 2 is this, and then where there's sine 2, we substitute that. This is going to be x over a squared, because a is a squared, root x squared minus a squared. So this is what we have. So if you can simplify this, we are going to get a squared over 2 cos inverse of x over a, and then here we are going to get let's see if we didn't, there's this 2 here, this 2, we left it out, this 2, and also this 2, because the 2 that comes with the identity here. So there's a 2, which means even here we are going to have 2x over a squared root x squared minus a squared, right? So if you are looking at this as minus, if you are looking at this expression, this and this will divide. So you're going to have minus x over a squared root x squared minus a squared. So this expression, what does this mean? If you are given an integral of this form x squared minus a squared, you should know that you can evaluate it in this form: a squared 2 cos x over a minus x over a squared root x squared minus a squared plus c. So now, if you're given an integral of this form dx, an integral of this form, you can just substitute the value of a in this expression, then you've evaluated the integral. So this is one other integral techniques that we have been looking at. So I'm going to do